All right, so last time we got into a few of the different formulas. So you guys remind me, which formulas do we know so far? If any. Which ideas do we know about probability? All right, good. I like it. Sweet. That's nice. I'll work with that. So you got two keywords, and or. And they both mean basically very different things. Or means what, for the most part? Or means addition. I love it. Because or is inclusive. It says it could be this, or this, or this, and I'll let you in. I always have in my mind like the nice bouncer. Right? The only way to get my nightclub is to be this, or this, or this, and he lets more people in. The mean bouncer is the and. Right? You got to have a lot of money, and you got to be wearing the right clothes, and this and that, and this and that, and then fewer and fewer people can get in. You with me? Okay, a little bit. So probably A or B. Which kind of makes sense. Like that very first one we did with or was getting a jack or an 8. And it kind of makes sense to people without, before we even talked about this, was just there's 8 cards now that'll work, not just 4. So that's my probability doubles to find that. So it's going to be A plus B, the probabilities. But then what do I have to do? Minus A and B. And why do we do that? Because we don't want to
double F.
What do we not want to do? That's cool. Why do we subtract that? You don't want to double count. I don't want to double count anybody. So Jack or 8, there are no cards in a normal deck of cards that are both, right? You can't turn it and make it into an 8. You'll be caught doing that. You don't want to do that. But you can be a jack and a club, for example. Right? So if I count all the jacks and I add in all the clubs, I've counted the jack of clubs twice. So that's why I would subtract 1. Because there's one card that's a jack and a club. How are we doing so far? Okay. We talked a little bit about, and I don't think I really finished this idea out, but and is basically multiply, but only if A and B are independent. Only if one does not affect the other one. Okay, so far so decent. So this is kind of nice. It's a nice analogy. Or is basically add, but you have a little adjustment to make in case they have some overlap. And is basically multiply, but we're going to talk right now about the adjustment you have to make in case they're not independent of each other. So an example of something that would be independent is Jack and 8. Right? They don't affect each other. Now let me get a little more specific here. Last time we did the whole silly example with me walking down and getting slapped on the face. Right? Thankfully it didn't happen. But that was to illustrate that this multiplication makes sense. I'm going to multiply these probabilities. We talked about the O-rings on the space shuttle. That thankfully I was not as traumatized because I wasn't actually watching it happen when I was a little kid. You multiply the probabilities. That's why you put multiple locks on your door. The probability somebody can get in should be smaller and smaller and smaller. With me? Okay, and I multiply things that are less than 1, my answer gets smaller. Cool. So the piece we're missing is to go back and talk about, and let me put this up here. This symbol here means given, in case I write that down or in case the book has that. That line there, that means given. A given B. So if I said, what's the probability I pick a king given it's a face card? We did this one last time. This line does not mean divide. You don't divide probability of king by probability of face card. That's not what it means. It means that given. Right? And that's given is kind of a different idea. What would go on the bottom?
12 face.
12 because it's face cards. This is how many face cards there are, right? So the bottom is always going to be related to what I know. Makes sense. That's why if I don't know a damn thing, the bottom is everything. I got to cover my ass and just say everything could happen. Here I know it's a face card. Only 12 things can happen. On the top goes what?
4.
4, because I still have all my kings. And real quick, notice what's the probability of a king by itself? Just what's probably get a king?
4.
4 out of 52. Which reduces to 1 out of 13. So, of course, it makes sense. If I know it's a face card, the probability that it's a king should, of course, get larger. Right? Does that make sense? If I know it's a face card, the probability that it's going to be a king is suddenly bigger. Because there's less stuff it could be. You guys kind of with me? No? Shit. All right. Now remember this. What about probability jack given club? What was that? What goes on the bottom now? 13. So what goes on the top?
4.
Not 4. Careful. We know it's a club. So the only way it can be a jack is if it's that one jack club. So one that's both. Well, what's the probability of a jack by itself?
4.
Which reduces to 1/13. So what's the difference between this situation here? If I tell you it's a face card, suddenly this probability changed, didn't it? By itself, the probability is 1 out of 13. If I tell you it's a face card, the probability goes way up. Over here, probably a jack is 1 out of 13. If I tell you it's a club, did the jack care? Did the probability change?
No.
So this situation is independent. And this situation is dependent. Depending on whether or not it's a face card, the probability it's a king changes. Right? They depend on each other. Whereas the jack, if I tell you it's a club, the probability is a jack is still the same. It's still 1 out of 13. So that's what those words mean in statistics. Dependent, independent. That's what those two words mean. Okay. So now the next step is to tie this together somehow with this. I think that's where I kind of left off last time. I tried to get you guys to give me a given formula. I think we got this up on the board, but it didn't make that last connection. So if I were to probably A given B, remembers what goes right on the bottom. What's got to go down there? B, something related to B. So B, the probability of B.
Probability A and B.
Good. The only way the top could be true, the only way it could be A is if it's also B, because I know the damn thing's at least B. Now, the sentences you end up creating when you're teaching statistics are very strange sentences. Right? The only way it could be A is if the damn thing's B, because I know it's B. So, okay, wait a minute. Let's break that thing down. But you guys kind of with me? I know this thing is B, whatever B is. B might be club. B might be face card. B might be Harley rider. Right? Whatever the hell B is, I know that's true. The only way it could also be A is if it's A and B. Because every damn thing in this problem is B, because I know that's true. So if I said, what's probably you're a Republican given you're a woman? Well, the bottom is going to be the number of women. And the top is not going to be all Republicans. The only way that they could get in there is if they are a Republican and a woman, because I know the person is a woman. So that's why the top is, they got to be A and B. So that's the formula for a given. And I don't know if you've noticed this yet or not, and this is not always necessarily true, but in statistics, the probability formulas look worse than the actual working of the problem is, right? I don't know if, I'm sure you all like, every damn formula looks worse than, but that's because formulas try to capture the most general situation. But we did several of these, and they were pretty damn easy. I would just put the number on the bottom, put the number on the top, I'm done. But this captures the idea of what we're doing. So that's this. Now let me see if anybody, all right, here we go. Here's the algebraic leap to take. Can anybody see a way to use that formula to get another way to look at probability of A and B? I have one thing here, but it's only if they're independent. So this would actually give me something more general. Right? Do you see probability A and B in there? Yes, good. That's the right answer. It's right there. Now how do I solve for that? using some algebra.
Bring the
Good.
probability of B to the other side.
Yeah, multiply that by, so if I multiply this by probability of B, it'll come up here. You guys cool with that? If I multiply that up, bam. You guys see that? Okay, maybe. So now what's the difference? What's the one difference between this formula, and I desperately, this formula is only true if what?
Independent.
If they're independent. If they don't affect each other, that's why there's no influence. That's purely A times purely B. They don't influence each other. What's this formula say? Probably A and B equals probability of one of them times probability of the other given the one of them. So tell me this. If they are independent, what's true? If A and B are independent, what is the probability of A given B? If they are independent, another way of thinking about that is they don't care about each other. If one happens, the other one doesn't care. The probability doesn't change. Right? So if somebody in New York right now ate too much at lunch and started to feel sick, are we going to care? No, unless you know the person, but we don't know this person. Whoever this person is in New York, somebody, I don't go, feel a disturbance. No. Right? So they're independent. Whatever I'm going to do is not affected by that happening. So what would be true here? Does the probability of A change given that B happened if they are independent? They don't care about each other. No, it's just like the probability of Jack was 1 out of 13. Probably a Jack given clubs. 1 out of 13, it didn't change. They are independent of each other. If one happens, the other one doesn't care. So this would stay that way. So the general rule for AND, is the probability of A and B is probability of A times probability of B given A. Because what does this become if they're independent? If they're independent, what is probably B given A? Does B care? So if independent, probability of A and B equals probability of A times probability of B. Because B doesn't care that A happened. Alright, so now I'm going to give you what you're desperately hoping for right now, and that is like, please, through God, give me a concrete freaking example. Right, I'm sure some of you guys are like, that would be really nice if I could see something concrete with this. So let's do the most simple, basic probability example you can, which would be I put 6 red chips and 12 green chips into this bag, right? This is very exciting. It's not exciting at all, but at least it gives us the idea. And let's say I pick, just to make sure everybody's on the right page, pick one chip. What's probably is red? Yeah, be careful. So 6 out of 18, which is 1/3. So I got a 1/3 chance of getting a red chip. What are all the things that could happen, by the way? What's called, it's the sample space. This is just the collection of all things that could happen. Of all, let's say, all outcomes. We did this the other day with the girl, boy. Remember that thing? We made that long list. Girl, boy. We tried to do it systematically so we didn't forget anybody. So what's the collection of all the things that can happen? This is kind of silly for one chip. It's going to look really amazing. The only things that could happen would be a red chip or a green chip. Well, that's exciting. So what if I pick 2 chips? What would it look like? Red. I love it. Which always somehow reminds me of The Shining. Red-green. Green. Green-red. I love it. Sweet. So it wasn't a very large sample space. We didn't have to be too careful about the system we used to make it. Right? If we went to 3, then you want to be very specific so you didn't forget anybody. Why are there 4 outcomes? Why do you think? And I love the answer. It's going to be, is that so many, dude? I don't know. Well, how many options? If I pick 2 chips, how many options for the first chip? 2. How many options for the second chip? 2. So for every 2 of these, there's 2 of those. 2 times 2 is 4. So how long would it be for picking 3 chips? 2 times 2 times 2. So that would be 8. And I don't know if you remember from the other day, we got 8 outcomes for 3 kids. Girl, boy, girl, boy. You guys kind of with me? Okay, good, good. So here's where things get a little weird with the 2 chips. If I pick 2 chips with replacement. So what that means is I would take a chip out, I'd look at it, and then I put it back in before I pick the next one. Now that becomes very important. Some of you guys might realize why. If I took a chip out and threw it away, how many chips are left?
1 less.
Yeah, 1 less. There's only 17 chips. Now what happens to my probabilities? They all change. So this one is with replacement. If I take 2 chips with replacement, what's the probability of green, red? And what's the probability of red, red? Not red dead. Red, red. So here's the idea. What's really hiding? What word is hidden? Because this word very often gets hidden. I get a green and a red. So I know that this is an and. These are both and situations.
Multiply the probabilities.
I love it. Are these going to be independent? If I pick one and then put it back in, will the next thing care what happened first? No. It's only if I take one out and threw it away. Now, all these guys are like, oh, shit. They all care about that. It's one dude, who knows, went somewhere else. Out of the world. So, this would be probability of green times probability of red. That's how you can break that up. So, it's probably get a green chip.
1/3.
Green chip, yeah. So 2/3, right? 12/18, which would be 2/3. Let's probably get a red chip. 1/3, 6 out of 18. So I get 2/3 times 1/3 is 2 9. There we go. Multiply. Not too bad, right? It's not too bad. I mean, if you can imagine now, if I picked 8 chips, you just do the same damn thing, but you'd have 8 pieces that you'd multiply. You with me? That's not, so this idea is easily extendable. Doesn't change. The idea doesn't change. What about red, red?
1/3.
Yeah, what's probably the first one's a red chip?
1/3.
Yeah, 1/3. You guys with me? It's probably the next one's a red chip. Still 1/3, because I put that first one back in. So I get 1/9. I like it. I like it. Now notice, this is what we said earlier. If I just look at this and I'm not careful, I could think that the probability red, red is 1 out of 4. Why would I think that might be true? Because there's 4 things. But why is it not 1 out of 4? We just proved it's not 1 out of 4. Why is it not 1/4?
Because red probability is different than green.
I love it, because they're not all equally likely. In fact, red, red is going to be the least likely, because there's the much fewer red chips, right? You guys kind of with me here? This all kind of comes back together? Okay. At least most of you are looking this way. This is good. Okay. So, what gets interesting is what happens if I do this without replacement. So we'll do these probabilities again. Green, red, and red, red. We start to see the pattern for this. The actual work is a little easier than the concept and the formula makes it look. The actual work was pretty nice. So the first chip, have I done anything yet? I haven't picked, so I pick it. What's probably I'm looking at a green chip? 2/3. I love it. You with me? We know the green is 2/3. Now let me do it like this though. Let me just do this. We'll just do it, Jeff. 12/18. Let me just put it like that. I'll show you why. It actually makes it a lot easier if you don't reduce, believe it or not. So I throw that one away. Woo. So what's probably the next one's going to be red?
17.
Yeah, there's 6 red out of 1 less chip. So I get 2/3 times 6/17. 3 goes into 6 twice, so I end up with 4/17. How are we doing so far? Is that all right? So it's basically the same. It's the same work I did here, except this second probability changes. That second probability changed because it depends on what I picked first. Why didn't the top change?
Because there's still 6.
Yeah, I didn't do anything with reds. It's the green that I picked and threw away, right? What about this one? Red, red. The first one is red. What's that going to be?
6/18.
Good. 6 out of 18. And then throw it away or feed that to my little brother.
5 out of 17.
6 out of 17.
5 out of 17.
5 out of 17. Why 5? Because the first one is red. What was it? The first one is red. So it's 1/3 times 5/17. So it's 5/51. How we doing? Real quick, what is this? 2/9 is about 22.2%. Right? It's really good to know 1/9 is 0.1111, so 2/9 is 0.22222. What is 4 divided by 17? Somebody help me out. It's going to be a little less than 0.25. It's going to be like 0.235. So if I do this without replacement, the probability went up a little bit, right, from what it was. What happens with the red, red? This is 11.1%. What's 5 divided by 51? It's a little less than 0.1. 0.09, so 9%, roughly. 0.98?
Yeah.
9.8.
Yeah, we'll say 9.8%. All right. And that probability went down a little bit. Now, it should kind of make sense. It should make sense to get 2 reds. It's going to be harder to get 2 reds if I pick one and throw it away. Because if that's a red, now there's fewer reds left. But here, to get a green and then a red, if I find a green and throw it away, there's a better chance I'm going to get a red now. There's fewer greens. So that actually makes sense how those probabilities changed. Do you have to know any of what I just said? Not really. It's nice. You have to know how to do this kind of problem. Okay. So I could do it with a deck of cards. If I pick 2 cards without replacement, let's probably get an ace and then king. What would that be? Bless you. Yeah, without replacement. Good. So completely depends. Be really careful when I give you that quiz that you make sure which situation you're in. So this is without replacement. I don't put the card back in. I throw it away or feed it to my other little brother. I have 2 of them. I can distribute the stuff. What's this first piece?
4 52.
Yeah, 4 to 52. That probably we're getting tired of seeing. But what happens to this guy?
4 out of 51.
Good. Well, I still have all 4 kings, but I got 1 less card because the minute I get here, I picked a card and threw it away. So see, the actual nuts and bolts work by itself makes more sense, but the formula is always going to look worse because it's trying to capture the idea behind all of it. So then you get 1/13 times 4 to 51, which is 4 out of
663.
663. Sounds about right. Okay. So I'll tell you what. I've been talking a lot.